Good evening, dear students. Yes. Okay, so in the last class, we have completed. Okay, so what all things we have discussed? So we have discussed about the alcohol phenols, right? Then we have seen the chemical properties, right? We have seen the chemical properties, that is the cleavage between the reactions involving the cleavage at the CO bond and the cleavage at your OH bond. So, right, so these chemical reactions we have seen for alcohols, right? Then, what all things we have discussed again? Then we have seen the acidity of alcohols, right? We have seen the acidity of alcohols, reactions with the metals, right? Then we have discussed about the esterification reactions or different esterifications reactions we have discussed. Okay, so let me. Yes. So these esterifications reactions we have discussed, right? Then we have discussed the reactions which involves the breakage of CO bond, that is the reactions with hydrogen halides, right? Reaction with hydrogen halides. So when alcohols react with the hydrogen halides, they form what? They form alkyl halides, right? So this we have discussed. Then we have seen the Lucas test, okay, to distinguish between the primary, secondary, and tertiary alcohol. So what is Lucas reagent? Yes, what is Lucas reagent, students? Lucas reagent is concentrated HCl and anhydrous ZnCl2, right? Concentrated HCl and anhydrous ZnCl2. Okay, so by using that, so when it is treated with primary alcohol, what it gives, it does not give any PPT. Okay, when it is reacted with secondary alcohols, when they react with your when it reacts with the Lucas reagent, it gives you turbidity, but after 5 minutes, right? After 5 to 10 minutes, it gives you the turbidity, right? Yes. So then tertiary alcohols, when they react with the Lucas reagent, they give you immediate, right? The turbidity or the PPT is formed immediately. So these are the your what reactions with the Lucas reagent. Then we have seen the reaction with phosphorus trihalides. So alcohols, they react with phosphorus trihalides to give you alkyl halides, right? Then we have seen the dehydration reaction, very important dehydration reaction also we have seen, right? So this is a dehydration reaction. So alcohols, they undergo dehydration to form alkenes on treated with a protic acid. You can take any protic acid, okay, and you're using the catalyst. Okay, so this is the reaction. So mechanism is very important as we have discussed. Okay, so this mechanism is also very important. So it is a important question. Okay, 3 marks compulsory question to explain the mechanism. So this also we have seen. So it involves 3 steps. First step is protonation of ethanol. Second step is formation of carbocation, and third step is elimination of a proton. Okay, so these are the 3 steps which are involved, right? Then after this, what we have seen? We have seen the oxidation and dehydrogenation reaction. Okay, oxidation means what? Oxidation means addition of oxygen. Dehydrogenation means removal of hydrogen. Okay, so we have seen the oxidation for primary, secondary, and tertiary alcohol. So when primary alcohols are oxidized, they will give you aldehyde. Okay, first, and then if you again oxidize it further, it will give you carboxylic acid. Then when you oxidize the secondary alcohol, so secondary alcohols, when you oxidize, you get the ketone. And tertiary alcohols, yes, it will give you what? Tertiary alcohols on oxidation, okay, as they do not have alpha hydrogen, okay, but what will happen? So, but when you, the strong, if you are using very strong oxidizing agent, okay, and the temperature also it should be very high, so it will give you a mixture of carboxylic acid and alcohol. Okay. So yes, so this is the reactions which we have seen. Then we have also seen the dehydrogenation also. Okay. Then we have seen few reactions for the these are the reactions which we have seen for phenols. Okay, reactions of phenols, that is Rimmer-Timmer reaction. what we are doing in Rimmer-Timmer reaction, students? Alcohols, sorry, your phenols, we are converted into salicylaldehyde. So what are the reagents which we are using? Chloroform in the presence of aqueous NaOH. Okay, chloroform in the presence of aqueous NaOH. Okay, you are going to get an intermediate. Further, doing base hydrolysis, you are going to get what? Salicylaldehyde. Okay, so this is a Rimmer-Timmer reaction, very, very important reaction, Rimmer-Timmer reaction. Next, we are seeing is a cold-base reaction. So they'll ask you, explain cold-base reaction with the equation. So what we are doing in cold-base reaction, we are taking phenol, and this phenol is converted into sodium phenoxide. So sodium phenoxide, we are heating. Okay, we are heating with carbon dioxide. The temperature will be about 400 Kelvin. Okay, and the pressure maintained is 6 to 7 atmospheric pressure. And what it forms? It forms an intermediate, that is sodium salicylate. This sodium salicylate further, okay, on acidification, it will give you what? It will give you the salicylic acid. So it will give you salicylic acid. So these are the, so this is a cold-base reaction. So again, very, very important name reaction. So Rimmer-Timmer reaction also we have seen. Okay, then is the Friedel-Crafts reaction. Okay, next is the Friedel-Crafts reaction, which we have seen. That is, it is an electrophilic aromatic reaction. Okay, so we are taken anisole, we are reacted with the alkyl chloride in the presence of anhydrous AlCl3. So we are going to get ortho and para substituted product. And always the para substituted product are more, they are like more stable, or you can say it is a major product. Okay. And this is a acyl group. So this is a acyl group. So, and this is a alkyl group. So this is alkylation. This is acylation. So acyl group will get attached to the acyl group will get attached to the ortho and para position with respect to the methoxy group. Okay. So next we will see a few more reactions which are there. Yes. So let me explain you. A few more reactions are there for phenols. So next is the electrophilic aromatic substitution we have seen for Friedel-Crafts reaction. So there are a few electrophilic substitution reaction, aromatic substitution reaction. First is the nitration. So in nitration, which is the nitrating agent which we are using, it is concentrated at HNO3. Okay. So by using concentrated HNO3 and H2SO4, what we are going to get? We are going to get nitronium ion. Okay, NO2 plus. Okay, NO2 plus. So that is the So how will happen? So we are going to take phenol. Okay, there is a phenol. So two molecules of phenol. What will happen? They'll react with dilute HNO3 with dilute HNO3. Okay, at 293 Kelvin. What we are going to get? We are going to get the we are going to get what? OH and NO2 plus OH and NO2. So which is major product? This is the major product, that is paranitrophenol. Okay, and this is the minor product. And this is water. Okay, product is water. So this is the nitration reaction. So phenol will react with dilute HNO3 at low temperature to give you mixture of ortho and para substituted phenol. Okay. Then if we use this phenol, okay, by using this phenol, okay, so if we use this phenol in with the presence of concentrated, so this is a dilute HNO3. So if we use it in the presence of concentrated HNO3, okay. So what will happen? So it will give you a ortho para directed product. Okay. So it is going to give you a tri. So one. So this is 2 and 3. So it is trinitrophenol. Okay, trinitrophenol, which is called as the picric acid. So they'll ask you, give the formula for picric acid. Okay, write the structure for picric acid. So this structure you have to write. So how you are going to get? So you are going to react your phenol with concentrated HNO3. Okay, with concentrated HNO3. Okay, so you are going to get what? 246. So it is 246 dinitrophenol. Okay, 246 dinitrophenol, which is known as the picric acid, which is known as what? Picric acid. Okay, so this is a very, very important reaction. So please remember this. So we have seen the nitration, that is with the dilute acid and with concentrated acid. Now, next is halogenation. So here we are carrying out the halogenation, that is with respect to bromine. So when we are using halogen as bromine, then it will undergo bromination. Okay, so let us take again two molecules of phenol. Okay, two molecules of phenol. So react it with bromine, react it with bromine in the presence of carbon disulfide. Okay, at 273 Kelvin, what I'm going to get? I'm going to get a orthopara. So ortho one, okay, and this is para, OH and Br. So this is orthobromophenol. This is orthobromophenoil, and this is para bromophenol. Okay, this is orthobromophenoil and this is parabromophenol. So plus 2 HBr, plus 2 HBr. So this is a halogenation reaction. Okay, this is a halogenation reaction. So what we are doing? Phenol, we are reacting it with bromine. We are using a non-polar solvent, okay, CS2, or you can use chloroform, or you can use carbon tetrachloride, okay, and the temperature is very low. Okay, and it will give you mixture of orthobromophenol and parabromophenol. So again, which is a major product? This is the major product. Okay, then next is again phenol. Okay, very important. So phenol, we are reacting it with what? We are reacting with 3 molecules of bromine. Okay, in the presence of water. So that is phenol is reacted with bromine water. Phenol is reacted with what? Bromine water. Okay, phenol is reacted with bromine water. And what it will give you? It will give you a product which is white, which is having a white PPT. Okay, so it is a 246. Okay, 246 tribromophenol. Okay, it is 246 tribromophenol. Okay, 246 tribromophenol. So this is the name. Okay, and it says white in color. So it will give you a white PPT, curdy like PPT. Okay, so this is another reaction. So very important. Okay, very important. Picric acid structure they'll ask, and they'll ask phenol reacting with bromine water. What is the product formed? Like that, the question will be asked. So we have seen pole-based reaction. We have seen the Rimmer-Timmer reaction. So in Rimmer-Timmer reaction, we are preparing what? Salicylic acid. Then reaction of phenol with zinc dust. Okay. Next reaction. So we are taking phenol. Okay. Reaction of phenol with zinc dust. Okay, with zinc dust. So let us take phenol. So this is the phenol. Okay, this is a phenol. React it with zinc. Okay, react it with zinc. What I am going to get? Okay, so I am going to get what? So I am going to get benzene plus ZNO. So I'm going to get benzene and ZNO. So phenol, okay, it is converted to benzene on heating with zinc dust. So you're going to heat it with zinc dust, you're going to get benzene. So 1 mark question, it can be asked, okay, phenol plus zinc, what is the product obtained? Okay, you have to write benzene. Then, so reaction, or we can write oxidation of phenol. Okay, oxidation of phenol. So next reaction, oxidation of phenol. Okay. So write the structure. So phenol, okay, phenol is there in the presence of Na2Cr2O7, H2SO4. Okay, heat. What I'm going to get? What I'm going to get? I'm going to get a para-benzoquinone. Okay, I'm going to get a para-benzoquinone. Okay, so this is the structure of para-benzoquinone. Okay. So this is the structure of para-benzoquinone. So benzoquinone. So this is also a 1 mark question, very important. Okay. So phenol, when you heat it, when you do oxidization, okay, in the presence of sodium chromate, okay. So phenol, when you react it with sodium chromate, so sodium chromate is an oxidizing agent. What do you mean by oxidation? It is providing oxidation. Okay, it is giving you oxygen, and it will remove what? It will remove the hydrogen. So what is happening here? So this hydrogen is removed and the oxygen is added. Okay, and so this is the product obtained, that is benzoquinone. Okay, it is a benzoquinone. So when phenol, when it is exposed to air, okay, what it happens, it slowly oxidizes to a dark pink color, okay, which contains the quinone. So this is the reaction. Yes. Next we are going to see about the ethers. Okay, next we are going to see about the ethers. So what are ethers? So these are the organic compounds which contains, okay, like this linkage, right? O like linkage. Okay, and how they are generally represented? They are generally represented like this. Okay, they are generally represented at this R and R dash. It can be your alkyl or it can be your aryl group. Okay, it can be your alkyl or it can be your aryl group. So what are ethers? So ethers, okay, they are having O linkage, that is ROR dash, and generally they are represented like this, and R and R dash can be your alkyl or the aryl group. So how it is further classified? Okay, how we can do the further classification of ethers? Okay, how we can do the further classification of ethers, students? So ethers are classified as simple, okay, or mixed. So simple ethers and another is mixed ether. So simple, or it is called as symmetrical ethers. Okay, simple or symmetrical ethers, mixed or unsymmetrical. Okay, mixed or unsymmetrical ethers. Fine. Okay. So what do you mean by simple now? Simple means, okay, both the alkyl groups are same. Okay, C2H5O, C2H5. So across the oxygen atom, the atom, okay, the this which is attached, okay, attached to the oxygen atom, the group which is attached to the oxygen atom is same. Okay, then we call it as simple, or it is called as a symmetrical ether. So across the oxygen atom, the group, if it is same, both the groups are same, then we call it as simple or symmetrical ether. Now, what do you mean by unsymmetrical ether? So, by this example, you will come to know. Okay, by this example, you will come to know. Okay, so this is the example. Okay, so here you can see across the oxygen atom. Okay, this is different. So this is a methyl group. This is a ethyl group. Okay, so it is a unsymmetrical ether. Across the oxygen atom, the group attached to the oxygen atoms are different. Then it is called as what? Mixed or unsymmetrical ether. Understood? Yes, is it clear? What are the classifications? Simple and mixed. Simple means across the oxygen atom, the group attached are same. Mixed means what? Mixed means the group attached across the oxygen atoms are different. Okay. Yes. Next, we are going to see the nomenclature. How to name this compounds. Okay. Next, we are going to see the nomenclature. Okay. Next, we are going to see the nomenclature. So, how we are going to name? So, common names, okay, of the ethers, they are derived from the names of alkyl or aryl. Okay. So, okay, like we are going to write separately first the in the alphabetical order. Okay, first or the whatever the alkyl this is there. Now suppose this is your this. So what I'm going to write? So how many? So there are two. So this is a methyl group, right? This is a methyl. So this is a methyl. This is a methyl. So how many methyls are there? Two methyls. I'm going to write dimethyl. Okay, and then the word ether. So this is a common name. Okay, now I want to write the IUPAC name. Okay, I want to write the IUPAC name. So the IUPAC name, it is named as alkoxyalkanes. Okay, it is named as alkoxyalkanes. So this is methoxy, methoxy, So, and the larger R group is taken as a parent hydrocarbon. So this is what? This is methoxymethane. Okay, this is methoxymethane. Suppose C2H5, O C2H5, how you are going to name it is diethyl ether. Okay, it is diethyl ether. And if it is IUPAC name, it is ethoxy, ethoxyethane. Okay, it is ethoxyethane like this. Okay, you are going to name the compound. Is it clear? Is it clear, students? Okay. Now, suppose I will give you, so this is little difficult, okay, because it is in cyclic form. So you can name this. Okay, so what is the name here? Yes, IUPAC name. So if I start numbering, I have to start numbering from here. So 1, 2, 3, 4, 5, and 6. Okay. Or I can, I can give the numbering like this. 1, 2, 3, 4, 5, and 6. Yes. Okay. So how we are going to name this now? So first, at one position, you have ethoxy. Okay, one position you have ethoxy. Then at two position, you have two methyl groups. So it is dimethyl. Okay. And you have what? This ring is cyclohexane. Okay. It is cyclohexane. So this way you are going to name the cyclic compound. Okay. Suppose I have like this. So C6H5 means what? C6H5 means your benzene. Okay, one I have a benzene compound, or you can name it as phenyl. Okay, or you can call it as benzene. And this is your ethyl. So how you are going to name? Common name will be what? You have to follow the alphabetical order. So it will be ethyl, phenyl, ether. Ethyl, phenyl, ether. Common name. And if I want to write the this, so it will be ethoxy benzene. Okay, ethoxy benzene. So like this is the IUPAC name. Got it? So the compound with the larger alkyl or aryl group, it should be taken as a parent compound. Okay. So like this, you are going to name. Yes. Next, we will see the structure of the functional group. Okay. So if I see the structure of a functional group, so this is your methyl. So what you can see here, between this, it is 117, 111.7. Okay, so what you can see in ethers, okay, around the sp3 hybridized oxygen. So oxygen is sp3 hybridized. Okay, oxygen is sp3 hybridized. There are 4 electron pairs. Okay, the 4 electron pairs, 2 are bonded and 2 are non-bonded. And these are arranged how? These are arranged tetrahedrally. Okay, due to the presence of these two bulkier groups. Okay, the presence of the two bulkier group, what is happening? The bond angle is increasing to 111.7 degree. Okay, and you can see the CO bond length. It is 141 picometer. So the CO bond length is 141 picometer. So due to the repulsion between these two bulkier groups, so bulkier groups are there, no? The bond angle is increased, okay, by 111.7 degree. Okay, so this is the structure of the functional group of your ether. So this you have to remember. Okay, so next we are going to see the methods of preparation of ethers. Okay, methods of preparation of ethers. So first is the first method of preparation is by dehydration of alcohol. Okay, by dehydration of alcohol. So here you can see. So first method is from dehydration. Okay, dehydration reaction. So I've taken CH3, CH2OH. Okay, reacting with concentrated H2SO4 at 443 Kelvin. Okay, what I'm going to get? I'm going to get ethene. And at 413 Kelvin, I'm going to get ether. Okay, so it depends. So alcohols, they undergo dehydration. Dehydration means what again? Removal of water. Okay, removal of water. Okay, in the presence of some acid. Okay, so it will give you alkene and ethers depending upon the temperature condition. So if the temperature is 413 Kelvin, you are going to get a ether. Okay, you are going to get a ether. If the temperature is 433 to 444 Kelvin, you are going to get a alkene. So depending upon the temperature, okay, I am going to get the products. Your alcohols, it will easily undergo dehydration in the presence of protic solvents. Okay, in the presence of your acids. Okay. So here they have given C. There is a ethanol. We are reacting it with concentrated H2SO4 at 413. So when it reacts with 413, I am going to get what? I am going to get a ether. So this is a diethyl ether. Okay, I am going to get a diethyl ether. Okay. Yes. So this is our dehydration reaction. Okay, dehydration reaction. Then next is the Williamson ether synthesis. Okay, next is the Williamson ether synthesis. So this is very important, Williamson ether synthesis, very important name reaction. Okay, mark it as important for 2 marks. Mark this important for 2 marks. Okay, very, very important. Mark this very important. So Williamson ether synthesis, in this reaction, what is happening? What are the reactants you have taken? One is the alkyl halide. Okay, one is the alkyl halide and another is the what? Sodium alkoxide. Okay, another is the sodium alkoxide. So what will happen? What will happen here? Your so what is happening? So I am going to take what? I am going to take a sodium alkoxide, okay, and I am going to heat it with your alkyl halide. So when this alkyl halide and sodium alkoxide reacts, what I am going to get? I am going to get a the byproduct is NaX plus R dash O R. Okay, so this is the ether. So this is the ether. Okay, so we are going to get what? So a reaction with alkyl halide with sodium alkoxide or sodium phenoxide is called as the Williamson's ether synthesis. Okay, so I am going to get alkoxide. So this is our sodium alkoxide. Okay, and this is our alkyl halide. Okay, this is our alkyl halide. So when alkyl halide reacts with your sodium alkoxide, I am going to get a ether and NaX. Okay, sodium halide. So this method is usually where it is used to prepare both type of ethers. That is your simple ethers as well as the mixed ethers. So both type of ethers can be prepared from this method. Okay, from Williamson's ether synthesis, both type of ethers can be prepared. Okay, then if I give you an example now. Okay, so let us take one of the example. So I have taken C2H5O A. What is the name, students? Can anybody tell me what is the name of this compound? It is sodium ethoxide. Right, it is sodium ethoxide. So sodium ethoxide reacts with what? It reacts with what? It reacts with the methyl bromide. Okay, this is methyl bromide. So what I'm going to get here? What I'm going to get? I'm going to get the byproduct as NaBr. Okay, I'm going to get the byproduct as NaBr and C2O5OCH3. So I have got a mixed ether, that is ethyl methyl bromide. Okay, ethyl methyl ether, sorry, ethyl methyl ether and sodium bromide. So this is the product. Okay, so this is sodium ethoxide reacting with methyl bromide to give you ethyl methyl ether and sodium bromide. Okay, another example I'll take with sodium phenoxide. Okay, I hope this is clear. No more confusion. Yes. Okay, so this is your what? This is your sodium phenoxide. Okay, this is your sodium phenoxide. So sodium phenoxide, I'm going to react it with methyl iodide. So this is my methyl iodide. So sodium phenoxide reacting with methyl iodide. What I'm going to get? So this Na will react with I. So I'm going to get NaI plus this I'm going to get OCH3. So it is methyl phenyl ether. Okay, methyl phenyl ether, or it is anisole. The name is anisole. Okay, the name is anisole. Okay, ethyl phenyl ether or ethyl phenyl ether or anisole. Yes, is it clear? Okay. So, depending upon the structure and cleavage of unsymmetrical ethers by halogen may occur either by SN2 or SN1 mechanism. So, the reaction, it depends upon the what type of structure is present. Okay, so it can occur by SN1 and SN2. So we have seen what is SN1 and SN2 in the your haloalkanes and haloarenes. Okay, yes. Okay, so next we are going to see the physical properties. Okay, next we are going to see the physical properties of ether. So these are all things we have discussed. Physical properties are not mentioned. Okay. So physical properties of ether. Okay. So dipole moment. Okay. First is the dipole moment. So when we are discussing about dipole moment, so we have seen the structure. So this is the structure of ether. So you can see that the ether has a angular shape. Okay, it has an angular shape, or we call it as it has a bent shape. Okay, or it is having a bent shape. Okay, and the CO bond, okay, in ethers it is polar. Okay, as a result, what will happen? There will be net dipole moment. Okay, so this is your R, this is your O, and this is your R. So this is having a bent structure, and oxygen has some. So the CO bond, it is a polar. So what it will do, it will tend to give the, there is a net dipole moment is added. Okay, so it will have some net dipole moment. Okay, next we are seeing the boiling point. So when we compare the alkane, okay, suppose we have a alkane CH3, CH2 thrice, CH3. Okay, then we have a diethyl ether. Okay, if I have a diethyl ether, and if I have a alcohol, that is CH3, CH2 thrice OH. So this is N-pentane. Okay, this is N-pentane. This is diethyl ether, and this is my butane. Okay, because four carbon and at one position you have alcohol. So all this, okay, so these are having almost same mass. Okay, but what you can see that in N-pentane, the boiling point is 309. Okay, in diethyl ether it is 307.6, and in butane alcohol it is 390. Okay, so due to the weak molecular forces of attraction between the ethers, so there are in ethers, there is weak forces are present. So they are having lower boiling point. Okay. Than your alcohols and your alcohols, right? So, but it is almost having the similar boiling point as compared to that of your what? As that of your alkanes. Okay. And all these three are having almost same molecular mass, comparable molecular mass. But when you see the boiling point of alcohol, it is higher because they are having strong molecular forces of attraction as compared to that of diethyl ether. They are having weak molecular forces of attraction. Next is solubility. When we are discussing about solubility, the ethers, okay, the solubility of ethers in the water is due to the fact that alcohols, okay, alcohols, the oxygen is there, right? So it can form the hydrogen bonding with water. So ether also, it can form the hydrogen bonding with water. So, but so you can see here, so how the ether is forming the hydrogen bonding with water. Okay, but what will happen to the solubility? It decreases. Okay, as from the lower member to the higher member. So as you go from lower to higher member, what will happen to solubility? It goes on decreasing. Okay, why? Because there is increase in the size of the alkyl group. So as you go further, okay, from lower to higher, what will happen? There will be increase in the alkyl group, and there will be some steric hindrance. Okay, bulkier groups will be there. So because of that, there will be steric hindrance. So steric hindrance increases, and the tendency to form the hydrogen bond with water goes on decreasing. So solubility of ethers in water is possible only for lower members. As you move further, the higher this, what will happen? The steric hindrance increases. As a result, the tendency to form the hydrogen bond also decreases. Okay, this is about the solubility. Next is density. Okay, next is density. All the ethers, they are lighter than water. Okay, they are lighter than water. Yes. So yes, so we were discussing about the physical properties of ethers. Okay, so we have completed. The dipole moment, boiling point, solubility, okay, and density. So density, all the ethers, as we have discussed, they are lighter than water. Okay, as compared to water, the ethers are lighter. Okay. Next, we are going to see the chemical properties. Okay, next we are going to see the chemical properties. So preparations we have seen. So let us go for the chemical properties of ethers. So properties of ether, it involves the cleavage of CO bond. So when you see the structure of ether, okay, how is the structure of ether? So the structure of ether is like this, right? R O R dash. So the reaction can occur like this, okay, or the electrophilic substitution reaction occurring in the aromatic ring. So reaction involves a cleavage of CO bond. Another is reaction, electrophilic substitution reaction occurring in the aromatic ring. Okay, so let us see the reaction involving the cleavage of CO bond. So first is with your hydrogen halide. Okay, so this is your hydrogen halide. So if you have a ether, so if I take ROR, okay, ROR dash, when it reacts with HX, okay, what I'm going to get? ROR dash, when it reacts with HX, I'm going to get RX plus ROH. Okay, I'm going to get RX plus ROH. Okay, so in symmetrical alkenes, what will happen? The cleavage, okay, of CO bond takes place under very drastic condition. Okay, and the HX, it will form what? Alkyl halide. When it reacts with your HX, it is going to form alkyl halide, and alcohol is given out. Okay, so this is the alcohol. So they have given the example of what? Ethyl, ethoxyethane. Okay, diethyl ether is given. Okay, so they have reacted with hydrogen bromide. What I have got? I have got your this what I've got bromoethane, and water is formed. Okay, so this is the reaction. So this is a reaction with hydrogen halide. So this is the first reaction, okay, which involves the cleavage of RCO bond. Okay, CO bond is nothing but, now this is CH3, okay, and this is CH3. So this bond. So this bond is breaking and a new bond is forming, right? New products are forming. So this is a reaction with hydrogen halide. Then even you can react. So this I have taken the symmetrical alkene. So I will give you an example of unsymmetrical alkene. Suppose I have an unsymmetrical alkene like your CH3, C, CH3, CH3, OCH3. What is the name here? It is tertiary, okay, tertiary butyl, okay, tertiary butyl methyl ether, okay, tertiary butyl methyl ether reacted with hydrogen iodide. What I'm going to get, students? What I'm going to get? I am going to get CH3, C, CH3, CH3, I plus what will be the alcohol? It will be CH3OH. So I'm going to get a tertiary butyl iodide, tertiary butyl iodide, and I'm going to get a methanol. Okay, I'm going to get a methanol. So with symmetrical alkenes and unsymmetrical ethers and symmetrical ethers, unsymmetrical and symmetrical ethers, you can obtain the your this what alkyl this halide. Okay, alkyl halide is obtained by reacting it with hydrogen halide. Okay. So next we are going to see the electrophilic substitution reaction. Okay, electrophilic substitution reaction. That is in electrophilic substitution reaction. Okay, the alkoxy group. This is the alkoxy group. The alkoxy group which is there. Okay, it is orthopara directing. It is also always what? It is orthopara directing. And what it will do? It will activate the aromatic ring towards the electrophilic substitution reaction. Okay, and what all we are going to do? We are going to do halogenation, nitration, Friedel-Crafts reaction. So let us see first the nitration. So we have taken anisole. We are going to do nitration. So nitrating agents are what? Concentrated nitric acid and concentrated sulfuric acid. So when concentrated nitric acid and concentrated sulfuric acid reacts, what is formed? Nitronium ion is formed, and this nitronium ion is a good electrophile. Okay, and that will react to what? This will react to your ortho and para position. So it will activate your aromatic ring. Okay, so I'm going to get what? I'm going to get the ortho para substituted product. So first is the I have got ortho nitroanisole, and here I've got para nitroanisole, and para compounds are more uh, stable. Okay, this is the major and this is the minor. So how the nitronium ion is generated from your nitrating mixture. Which is the nitrating mixture, students? It is concentrated HNO3 plus concentrated H2SO4 will give you the nitronium ion. Okay, next is bromination. Okay, bromination. So bromination reaction on anisole. Okay, we are going to do bromination of that is bromine in acetic acid. Okay, we are going to use bromine in acetic acid. So our electrophile is bromine. Okay, Br. So this will attack at the what? At the ortho and para position. So I'm going to get ortho bromoanisole and para bromoanisole. So again, your para is the major product. Okay, so next. So we have seen nitration, we have seen halogenation. Okay, now we are going to see the Friedel-Crafts reaction. Okay, let us see the Friedel-Crafts reaction. So in Friedel-Crafts reaction, that is OCH3. Okay, we have anisole. So anisole, what it is doing? We are reacting with methyl chloride. Okay, in the presence of anhydrous AlCl3. What I am going to get, students, here? What I am going to get? I am going to get the methoxy and this. Okay, so our this is electrophile is methyl group. Okay, methyl carbocation. So this will be the again ortho and para products we are going to get, and again the para is the most stable. So this is most stable or this is a major product. Okay, and in acylation, what is the electrophile? So again we are going to take this, we are going to get CH3 COCl in the presence of anhydrous AlCl3. Okay, what I'm going to get, students? I'm going to get your OCH3 and COCH3. Okay, plus I'm going to get OCH3 and COCH3. Okay, so this is again a para product. So acetyl chloride, we are reacting it with what? Acetyl chloride. So anisole is reacting with acetyl chloride. I am going to get orthomethoxy acetophenone. Okay, orthomethoxy acetophenone, and this is para methoxy acetophenone. Okay, yes. And this is also what? Orthomethoxy toluene, and this is para methoxy toluene. Okay, understood? So these are the Friedel-Crafts reactions. So Friedel-Crafts reaction always they take place in the presence of the and your Lewis acids. Okay, like anhydrous AlCl3. Okay, and your the alkyl group, or it can be your acyl group. Okay, which is the electrophile. Okay, and that will be acyl group or the alkyl group. It will be introduced on the ortho and para position. Okay, yes. Right. So next, there are some important alcohols which you have to know. So first is a methanol. Okay, you have to know about methanol. But methanol is called as the wood spirit. Okay, methanol is called as the wood spirit. So how it is prepared? Methanol is prepared by you're going to do a hydrogenation reaction. Hydrogenation means what? Addition of hydrogen. Okay, formed that is hydrogenation with the carbon monoxide. Okay, you are going to do hydrogenation on carbon monoxide. Okay, at a high pressure. So pressure is maintained at 200 to 300 atmospheric pressure. Okay, and at a temperature is also very high. That is 573 to 673 Kelvin. Okay, so and a catalyst is used, that is your ZNO and Cr2O3. What I'm going to get? I'm going to get the methanol. I'm going to get the alcohol, that is methanol, which is known as the wood spirit. So carbon monoxide, you are going to do catalytic hydrogenation formed from carbon monoxide at high pressure, okay, and temperature in the presence of a catalyst, okay, the ZNO and Cr2O3 to give you methanol. Then what are the properties? It is a colorless liquid, okay, and it is highly poisonous in nature, okay. It is used as a solvent in paints. Okay, it is used in varnishing and in the preparation of formaldehyde. So these are the properties of methanol. Okay, then next alcohol is ethanol. Okay, next is ethanol. So ethanol, how it is obtained? You are going to do fermentation, okay, of sucrose. You are going to do fermentation of sucrose. Okay, that is sucrose. It is what you are going to do in anaerobic condition, that is without the supply of oxygen. Okay, you are going to use an enzyme invertase. Okay, you are going to use the enzyme invertase. So by that you are going to convert your sucrose to glucose and fructose. Okay, glucose and fructose. Now what happened? This glucose and fructose, again, what I'm going to do, I'm going to use the zymase, enzyme zymase, and I'm going to convert it into ethanol. Okay, ethanol and carbon dioxide. So the enzyme zymase, okay, it is obtained from the yeast. And what it does, it converts your glucose, or you can use fructose into ethanol. Okay, so this is the reaction. So commercially, so this method is used at a commercial level. Okay, that is commercial means what? you can obtain it in a more quantity. Okay, it is obtained in more quantity. Okay. So this is about the ethanol. Then what are the properties of ethanol? This is also a colorless liquid. Okay. It is used as a solvent in your paints. Okay. Also, it is used for various preparation of carbon compounds. Okay. Then this commercial alcohol, it is made unfit. Okay, for drinking by adding some copper sulfate and pyridine. So this is also known as denatured alcohol. What it is called as denatured alcohol. So these are some of the important properties of ethanol. Is it clear? Okay. So this completes your chapter, alcohol, phenols, and ethers. So what all things we have discussed from this complete chapter? So first we have discussed the about the definitions, okay, of alcohol, phenols, and ethers. So what are these called as alcohol? Okay, what is the meaning? Okay, what are the what you say? What is the general formula? Okay, so these all things we have discussed about the alcohol, phenols, and ethers. Okay, so in then we have discussed about the classification. Okay, about the alcohol, phenols, and ethers. That is alcohol, phenols, and ethers. Also, we have discussed the classification. Okay, then we have seen the nomenclature. Okay, we have seen the nomenclature. Okay, so we have seen the nomenclature also, how to name the compounds, okay, how to name the alcohols, how to name the phenols, how to name the ethers. Then we have discussed about the structures of the functional group with respect to alcohols, with respect to phenols, with respect to your ethers, okay. Then we have seen the methods of preparations of alcohols, okay. So different methods we have seen, so these are the different methods which we have seen for preparation of alcohols. Then we have seen the methods of preparation of phenols also. So very important main reactions, okay. That is from haloarenes we can prepare from benzene sulfonic acid. So you need to know what is oleum. Okay, then from disonium salt, how to prepare. Okay, then how to prepare it from cumene. What is cumene? Okay, what is the process? What is a byproduct obtained? So these all things you need to know. Then we have discussed about the physical properties of alcohols and phenols. Okay, the various physical properties of alcohols are and phenols. Okay, yes, so these are all the physical properties which we have discussed about the phenols, alcohol, phenols, and ethers. Then we have seen the chemical reactions of alcohols and phenols. So where the reaction involving the cleavage of OH bond and the reaction involving the cleavage of CO bond. Also, we have discussed about the acidity of alcohols and phenols. Then we have seen the esterification reactions, so different esterification reactions. Okay, three methods with the alcohol or phenols when you react it with carboxylic acid, okay, with acetic anhydride and acid chloride, you are going to get esters, okay. Then we have discussed about the cleavage involving the CO bond, which are the reaction with hydrogen halides. Then dehydration mechanism is very important. Mechanism of dehydration, okay. Then also we have seen which all the different reaction, that is the Lucas test. Okay, then we have seen reaction with phosphorus trihalide, dehydration reaction, dehydrogenation, then oxidation. Okay, various reactions we have seen. Then we have seen the reactions for the phenols. Okay, that is Rimmer-Timmer reaction. Then we have seen Kolbe's reaction, Friedel-Crafts reaction. Okay, then we have seen the nitration. Okay, electrophilic nitration, that is electrophilic substitution reaction. Nitration when you use dilute, okay, we are going to get orthoparasaturated phenols, and when you use concentrated nitric acid, we are going to get trinitrophenol, that is picric acid, 2,4,6 trinitrophenol, picric acid. Then we have seen halogenation, okay, bromination. Then we have seen bromination, okay. So halogenation we have seen, then bromination we have seen, then coal-based reaction we have seen. Okay, so these different reactions we have seen. Then we have seen the reaction of phenol with zinc dust to give you benzene. Then we have seen oxidation of phenol also. Okay, then we have seen water ethers. Okay, water ethers. Then we have seen the electronic structure of ethers, then physical properties of ethers, classification of ethers, how to name the compounds, okay, name the, how to give the impact nomenclature for ethers. Then structure, we have discussed the structure of ethers, okay, how is the structure of ether, functional group ether. Then methods of preparation of ether, that is first we have seen by dehydration of alcohols, then we have seen by Williamson's ether synthesis, okay. So two important reactions we have seen of ether. Then we have also seen the physical properties, okay, dipole moment, then about the dipole moment, and we have seen about the boiling point, solubility, density. Okay, then we have seen about the chemical properties. Okay, chemical properties. Firstly, reaction with hydrogen halide. Okay, where the cleavage of CO bond takes place. Then electrophilic substitution reactions of aromatic ethers. Okay, we have seen nitration, halogenation, Friedel-Crafts reaction. Okay, so these main reactions we have seen. So these are things. Okay, and then we have discussed some of the this compounds. Okay, that is ethanol and methanol. So these compounds we have discussed. Okay, so yes, is it clear? Yes, so I hope you have understood all the concepts. Yes, fine. So these are the things, okay, which are included in this chapter, alcohol, phenols, and ethers. Okay, so this completes your chapter, alcohol, phenols, and ethers. And yes, so tomorrow we are going to start with the next chapter, that is aldehyde, ketones, and carboxylic acid. Yes. Okay. So by this, I shall end this session here. So we'll meet in the next class. Thank you.